What if everything you thought you knew about reality was just the tip of the iceberg? What if the universe is far stranger, more mysterious, and more interconnected than we ever imagined? Welcome to a journey that will stretch your mind to its limits as we dive into the mind-bending world of quantum mechanics and explore 30 theories that challenge everything we think we know about the universe. From parallel worlds to particles that communicate across galaxies, from the idea that our reality might be a hologram to the possibility that time itself is an illusion, this is not just science fiction. These are real, groundbreaking ideas that scientists are grappling with right now. And today, we're going to break them down in a way that's fun, fascinating, and maybe just a little bit mind-blowing. So buckle up, because by the end of this video, you might never look at the universe or even yourself the same way again. Let's get started. Now, let's step into the first theory that will completely reshape how you think about reality. Imagine this: every decision you make, no matter how small, doesn't just affect your life. It creates an entirely new universe. This is the many worlds interpretation, a theory that suggests every possible outcome of a quantum event actually happens, but in a separate, parallel universe. It's not science fiction. It's a serious idea proposed by physicist Hugh Everett in the 1950s. At its core, this theory challenges the idea of a single, linear timeline. Instead, it paints a picture of an infinite web of universes, each branching off from every possible quantum decision. Think about it. Somewhere out there, there's a version of you who made a different choice, leading to a completely different life. But how does this work? In quantum mechanics, particles exist in a state of superposition, meaning they can be in multiple states at once until observed. The many worlds interpretation takes this a step further, suggesting that when a measurement or decision is made, the universe splits into multiple versions, each reflecting a different outcome. This means there's no single collapse of possibilities into one reality. Instead, all possibilities exist simultaneously, just in different universes. Proponents of this theory argue that it solves some of the biggest puzzles in quantum mechanics, like the measurement problem, by removing the need for an observer to collapse the wave function. But it also raises mind-bending questions. If every decision creates a new universe, how many versions of you are out there? And what does that mean for free will, destiny, or even the nature of existence itself? The many worlds interpretation doesn't just challenge our understanding of time and reality. It forces us to rethink what it means to be a part of this vast, interconnected multiverse. And as we'll see, this is just the beginning of the quantum rabbit hole. Now, let's unravel another mind-bending concept that takes us deeper into the quantum realm: quantum entanglement. Picture this: two particles, separated by vast distances, somehow remain connected in such a way that the state of one instantly influences the state of the other. This phenomenon, which Albert Einstein famously called spooky action at a distance, defies our everyday understanding of how the universe works. It's as if these particles share an invisible bond, communicating faster than the speed of light, something Einstein himself thought was impossible. But here's the kicker: this isn't just a theoretical idea. Scientists have repeatedly demonstrated quantum entanglement in experiments, proving that this strange connection is very real. So how does it work when two particles become entangled? Their properties, like spin or polarization, are linked no matter how far apart they are. Measure one, and the other instantly knows and adjusts accordingly. This instantaneous connection challenges the very foundation of classical physics, which assumes that nothing can travel faster than light. But in the quantum world, the rules are different. This has huge implications, not just for our understanding of reality, but also for the future of technology. Imagine a world where communication happens instantaneously without any delay, thanks to entangled particles. It could revolutionize everything from secure messaging to quantum computing, but it also raises profound questions about the nature of space and time. If particles can influence each other across vast distances, does that mean space is just an illusion? Or is there some deeper, hidden layer to reality that we're only beginning to glimpse? Quantum entanglement doesn't just challenge our understanding of physics, it forces us to rethink the very fabric of the universe. And as we'll see, this is just one piece of the quantum puzzle that continues to baffle and inspire scientists today. Now, shifting our focus to another cornerstone of quantum mechanics, let's dive into the Copenhagen interpretation. This theory, developed in the 1920s by Niels Bohr and Werner Heisenberg, is one of the earliest and most influential frameworks for understanding the quantum world. At its heart lies a radical idea. The role of the observer is not just passive but fundamentally shapes reality itself. Here's how it works. In the quantum realm, particles don't have definite properties until they're measured. Instead, they exist in a superposition, a blend of all possible states. But the moment an observation is made, this superposition collapses into a single, definite state. This is what's known as wave function collapse. Think of it like flipping a coin. While it's in the air, it's neither heads nor tails but a mix of both possibilities. Only when it lands, when you observe it, does it become one or the other. The Copenhagen interpretation suggests that reality, at its core, is probabilistic, not deterministic. This was a huge departure from classical physics, which assumed that the universe operates like a clockwork machine, predictable and fixed. But the Copenhagen interpretation doesn't stop there. It also introduces the idea that the act of measurement itself is inseparable from the outcome. In other words, the observer and the observed are deeply intertwined. This has led to some fascinating and controversial debates. For instance, does this mean that consciousness plays a role in shaping reality? Or is it simply the interaction between the measuring device and the quantum system that causes the collapse? These questions have sparked decades of discussion, with some scientists embracing the Copenhagen interpretation as a practical tool for making predictions, while others criticize it for being incomplete or even philosophically unsatisfying. Despite the controversies, the Copenhagen interpretation remains a foundational pillar of quantum mechanics, shaping how we think about experiments, technology, and even the nature of reality itself. It's a reminder that the quantum world doesn't just challenge our understanding, it challenges us to rethink what it means to observe, to measure, and to know. And as we'll see, this is just one of the many ways quantum mechanics continues to push the boundaries of science and philosophy. Now, let's take a step into a theory that feels like it's straight out of science fiction, but is grounded in some of the most cutting-edge physics of our time, the holographic principle. This mind-bending idea suggests that our three-dimensional universe might actually be a projection of information encoded on a two-dimensional surface. Yes, you heard that right, our reality could be a kind of cosmic hologram. The origins of this theory trace back to the study of black holes. In the 1970s, physicist Jacob Bekenstein and later Stephen Hawking discovered that black holes have a property called entropy, which is related to the amount of information they contain. But here's the twist. This entropy isn't proportional to the volume of the black hole, as you might expect, but to its surface area. This led to the startling idea that all the information about what's inside a black hole could be encoded on its boundary or event horizon. Building on this, physicists Gerard T. Hooft and Leonard Susskind proposed that this principle might apply not just to black holes, but to the entire universe. They suggested that the universe itself could be like a hologram, with all the information about everything in it, stars, planets, even you and me, encoded on a two-dimensional surface at its boundary. In this view, our three-dimensional reality is just a projection of that information, much like a holographic image that appears three-dimensional but is actually created from a flat surface. But what does this mean for our understanding of reality? For one, it challenges the very notion of space and dimensionality. If the universe is fundamentally two-dimensional, then our perception of three-dimensional space might be an illusion, a kind of cosmic trick. It also raises profound questions about the nature of information itself. Is information the most fundamental building block of reality, more basic than matter or energy? The holographic principle has far-reaching implications, from the way we think about gravity to the nature of spacetime itself. Some scientists believe it could even provide a pathway to unifying quantum mechanics and general relativity, two theories that have so far resisted reconciliation. While the idea is still speculative and far from proven, it's a powerful reminder that the universe is far stranger and more interconnected than we often assume. As we continue to explore the mysteries of quantum realities, the holographic principle invites us to reconsider not just what we know, but how we know it. Could our entire existence be a projection, a cosmic illusion? It's a question that pushes the boundaries of science and philosophy, and one that keeps us looking deeper into the fabric of reality. And speaking of fabric, our next theory takes us into the realm of tiny vibrating strings that might just hold the key to everything string theory, but more on that in a moment. Now let's dive into a theory that might just be the ultimate cosmic symphony, string theory. Imagine the universe not as a collection of particles, but as a vast orchestra of tiny, vibrating strings. These strings, each one-dimensional and unimaginably small, are thought to be the fundamental building blocks of everything matter, energy, even space and time itself. At its core, string theory proposes that these strings vibrate at different frequencies, much like the strings of a guitar producing different notes. Each unique vibration corresponds to a different particle or force in the universe. For example, one vibration might create an electron, while another could produce a photon, the particle of light. This elegant idea suggests that all the complexity of the universe arises from the harmonies and rhythms of these tiny strings. One of the most exciting aspects of string theory is its potential to unify two of the greatest pillars of modern physics, quantum mechanics and general relativity. Quantum mechanics describes the behavior of the very small, like atoms and particles, while general relativity explains the very large, like stars and galaxies. But these two theories don't play well together. They've resisted unification for decades, leaving physicists searching for a deeper framework. String theory offers a possible solution by describing all particles and forces as manifestations of these vibrating strings, potentially bridging the gap between the quantum and cosmic scales. However, string theory isn't without its challenges. For one, it requires extra dimensions, not just the 3 spatial dimensions we're familiar with, but up to 10 or even 11 dimensions in some versions of the theory. These extra dimensions are thought to be curled up so tightly that we can't perceive them, but their existence is crucial for the math to work. This raises the question, if these dimensions are real, how do we detect them? Another challenge is that string theory is incredibly difficult to test experimentally. The strings themselves are so small that they're far beyond the reach of current technology. This has led some critics to argue that string theory is more of a mathematical framework than a testable scientific theory. Yet, despite these hurdles, research continues, with physicists exploring new ways to probe the theory's predictions, such as through high-energy particle collisions or observations of the early universe. String theory also opens up fascinating possibilities, like the idea of parallel universes or brains, higher dimensional objects that could exist alongside our own. Some versions of the theory even suggest that our universe might be a 3-dimensional brain, floating in a higher dimensional space, with gravity leaking into our world from these extra dimensions. While string theory remains a work in progress, it's a testament to humanity's drive to uncover the deepest truths of the cosmos. It challenges us to think beyond the familiar, to imagine a universe where the smallest vibrations create the grandest symphonies. And as we continue to explore, who knows what melodies we might discover. Next, we'll shift our focus to a theory that asks a question straight out of a sci-fi blockbuster. What if our universe is nothing more than a simulation? But more on that in a moment. Now, let's take a step into a theory that feels like it's straight out of a science fiction movie, but might just be closer to reality than we think. This is the simulation hypothesis, the idea that our universe and everything in it could be an incredibly advanced computer simulation. Imagine for a moment that everything you see, touch, and experience is nothing more than lines of code running on some unimaginably powerful computer. Sounds wild, right? But this idea has been taken seriously by philosophers, scientists, and even tech billionaires. The roots of this theory go back to ancient philosophy, with thinkers like Plato pondering whether reality is just a shadow of something greater. Fast forward to the modern era, and philosopher Nick Bostrom formalized the idea in 2003 with his now famous trilemma. He argued that at least one of these three statements must be true. 1. The human species is very likely to go extinct before reaching a post-human stage. 2. Any post-human civilization is extremely unlikely to run simulations of their ancestors. Or 3. We are almost certainly living in a simulation. If the first two aren't true, then the third becomes highly probable. But how could this even work? Well, think about the rapid advancements in technology. Video games today are light years ahead of what they were just a few decades ago, with virtual worlds becoming more immersive and realistic. If this trend continues, it's not hard to imagine a future where simulations are indistinguishable from reality. Some argue that if a civilization reaches a level of technological sophistication where it can create such simulations, it's likely they would run countless ones, making it statistically more probable that we're in one of those simulations rather than the original reality. From a scientific perspective, there are even attempts to test this idea. Physicists have proposed looking for potential glitches in the fabric of reality, tiny anomalies that could hint at the underlying code of the simulation. For example, some have suggested that the behavior of particles at extremely small scales, or the way light behaves in certain conditions, might reveal patterns that resemble the pixelation of a digital screen. So far, no definitive evidence has been found, but the search continues. Of course, the simulation hypothesis isn't without its critics. Some argue that it's untestable and therefore not a scientific theory at all. Others point out that even if we are in a simulation, it doesn't change the fact that our experiences feel real to us. And then there's the question of who's running the simulation and why. Are we part of some grand experiment or just a form of entertainment for a higher civilization? Despite the debates, the simulation hypothesis forces us to confront profound questions about the nature of reality, consciousness, and our place in the universe. It challenges us to think beyond the limits of our senses and consider the possibility that the world we know might be far more complex and far stranger than we ever imagined. Next, we'll explore a theory that takes the idea of alternate realities to a whole new level: quantum immortality. But more on that in a moment. Now, let's shift gears to a theory that's as fascinating as it is unsettling: quantum immortality. This idea suggests that your consciousness might never truly experience death, but instead it shifts to alternate realities where you continue to exist. It's a concept that sounds like it belongs in a sci-fi thriller, but it's rooted in the strange and counterintuitive world of quantum mechanics. The theory builds on the many worlds interpretation which we explored earlier. Remember how every quantum decision spawns a new universe? Quantum immortality takes this a step further by proposing that when faced with a life-threatening situation, your consciousness doesn't end, it simply branches into a reality where you survive. For example, imagine you're in a car accident. In one universe, the outcome is fatal, but in another, you walk away unscathed. According to this theory, your consciousness would always find itself in the reality where you live, no matter how unlikely that survival might seem. This idea was first popularized by physicist Max Tegmark, who used it to explore the implications of quantum mechanics on our understanding of life and death. It's a thought experiment that forces us to confront some deeply uncomfortable questions. If this theory were true, would it mean that we're essentially immortal from our own perspective? And what would that mean for our sense of self or even our morality? But let's be clear, quantum immortality is highly speculative and controversial. Critics argue that it's more of a philosophical musing than a scientific theory, as it's nearly impossible to test or prove. After all, if your consciousness only experiences the realities where you survive, how could you ever know about the ones where you don't? It also raises ethical dilemmas. If we believe in quantum immortality, would it change how we approach risk or even end-of-life decisions? Despite its speculative nature, the theory has captured the imagination of many, partly because it challenges our fundamental assumptions about life, death, and reality itself. It's a reminder that the quantum world is full of mysteries that defy our everyday intuition, and that our understanding of existence might be far more limited than we realize. Next, we'll dive into the multiverse theory, which takes the idea of alternate realities to an even grander scale, but more on that soon. Now, let's take a step into the vast and mind-bending realm of the multiverse theory. This idea takes the concept of alternate realities to an entirely new level, suggesting that our universe is just one of an infinite number of parallel universes, each with its own unique set of physical laws and possibilities. It's a theory that stretches the boundaries of our imagination, but it's also grounded in some serious scientific thought. The multiverse theory builds on the foundation of quantum mechanics, particularly the many worlds interpretation we discussed earlier. While the many worlds interpretation focuses on the branching of realities at the quantum level, the multiverse theory expands this idea to encompass entire universes. Imagine not just one universe where you made a different choice, but an infinite number of universes where every possible outcome of every possible event has actually happened. In one universe, dinosaurs might still roam the Earth. In another, you might be a world-famous musician. The possibilities are endless. This theory isn't just a product of wild speculation. It has roots in several areas of physics. For example, cosmic inflation, the rapid expansion of the universe after the Big Bang, suggests that our universe might be just one bubble in a vast foam of universes. String theory, another leading candidate for a theory of everything, also hints at the existence of multiple dimensions and universes. Even quantum mechanics, with its probabilistic nature, seems to leave the door open for the idea of a multiverse. But the multiverse theory isn't a single, unified idea. It comes in several flavors, each with its own unique twist. For instance, the Level 1 multiverse suggests that our universe is so vast that regions beyond our observable horizon might have completely different physical properties. The Level 2 multiverse proposes that entirely separate universes exist, each with its own set of physical laws. And then there's the Level 3 multiverse, which ties back to the many worlds interpretation, where every quantum decision creates a new branch of reality. What's truly fascinating is how the multiverse theory intersects with other quantum ideas we've explored. For example, it raises questions about the nature of reality itself. If every possible universe exists, does that mean all outcomes are equally real? And how does this theory fit with the concept of quantum entanglement, where particles can be connected across vast distances? Some scientists even speculate that entanglement might be a clue to how these parallel universes interact. Though this remains highly speculative, of course, the multiverse theory isn't without its critics. One of the biggest challenges is that it's incredibly difficult to test. If other universes exist beyond our own, how could we ever observe them? Some argue that the theory is more philosophy than science, while others believe it's a necessary framework for understanding the true nature of reality. Regardless of where you stand, the multiverse theory forces us to rethink our place in the cosmos and consider the possibility that our universe is just one small piece of an infinitely larger puzzle. As we continue our journey through the quantum landscape, we'll next explore the pilot wave theory, an alternative to the Copenhagen interpretation that offers a different perspective on the nature of particles and reality. But more on that soon. Now, let's shift our focus to a fascinating alternative to the Copenhagen interpretation, the pilot wave theory. This theory offers a completely different perspective on how particles behave in the quantum world, challenging some of the core ideas we've explored so far. Unlike the Copenhagen interpretation, which suggests that particles exist in a superposition of states until observed, the pilot wave theory proposes that particles have definite positions at all times, guided by an underlying pilot wave. The idea of the pilot wave theory dates back to the early days of quantum mechanics, when physicist Louis de Broglie first introduced the concept in the 1920s. Later, physicist David Bohm expanded on this idea, giving it a more robust mathematical framework. At its core, the theory suggests that particles are not just random entities, but are instead guided by a hidden wave that determines their path. Think of it like a boat being steered by an invisible current. The boat has a definite position, but its movement is influenced by the unseen forces around it. One of the most intriguing aspects of the pilot wave theory is how it reintroduces determinism into quantum mechanics. In the Copenhagen interpretation, the behavior of particles is inherently probabilistic, meaning we can only predict the likelihood of where a particle might be. But in the pilot wave theory, particles follow precise trajectories determined by the pilot wave. This means that, in principle, if we could know the exact state of the pilot wave, we could predict the exact position and movement of a particle at any given time. This deterministic approach has significant implications for our understanding of reality. It challenges the idea that the quantum world is fundamentally random and instead suggests that there's an underlying order we simply can't see. However, this doesn't mean the pilot wave theory is without its mysteries. The pilot wave itself is non-local, meaning it can influence particles instantaneously across vast distances, which raises questions about how it interacts with the principles of relativity. Another key difference between the pilot wave theory and the Copenhagen interpretation is how they handle the concept of wave function collapse. In the Copenhagen interpretation, the act of observation causes the wave function to collapse into a single state. But in the pilot wave theory, the wave function never collapses, it simply guides the particle along its path. This removes the need for an observer to play a central role in determining reality, which some find more satisfying from a philosophical standpoint. Despite its elegance, the pilot wave theory hasn't gained the same widespread acceptance as the Copenhagen interpretation. One reason is that it introduces additional complexity, requiring the existence of hidden variables, the pilot wave, that we can't directly observe. Critics argue that this makes the theory less elegant and harder to test. However, proponents believe it offers a more intuitive and complete picture of quantum mechanics, free from the paradoxes and uncertainties of other interpretations. As we continue to explore the quantum landscape, the pilot wave theory reminds us that there's still much to uncover about the nature of reality. It challenges us to think beyond the mainstream and consider alternative explanations for the strange behavior of particles. Next, we'll dive into the phenomenon of quantum tunneling, where particles defy classical physics by passing through barriers they seemingly shouldn't be able to. Stay tuned, it's going to get even more fascinating. Now, let's venture into one of the most mind-bending phenomena in quantum mechanics, quantum tunneling. This is the bizarre ability of particles to pass through barriers that, according to classical physics, should be completely impenetrable. Imagine throwing a ball at a wall, only for it to magically appear on the other side without breaking the wall. That's essentially what happens in the quantum world, and it's as strange as it sounds. At the heart of quantum tunneling is the wave-like nature of particles. In quantum mechanics, particles aren't just tiny solid objects, they also behave like waves, spreading out and existing in a range of possible states. When a particle encounters a barrier, its wave function doesn't abruptly stop at the barrier's edge. Instead, it extends into and even beyond the barrier, meaning there's a small but real probability that the particle can appear on the other side. This isn't just theoretical, it's been observed in countless experiments and plays a crucial role in both nature and technology. One of the most significant applications of quantum tunneling is in nuclear fusion, the process that powers stars like our Sun. In the core of a star, hydrogen nuclei need to overcome a massive electrostatic barrier to fuse together and release energy. Classically, the nuclei don't have enough energy to break through this barrier. But thanks to quantum tunneling, there's a tiny chance they can tunnel through it, allowing fusion to occur and stars to shine. Without this quantum phenomenon, the universe as we know it wouldn't exist. But quantum tunneling isn't just a cosmic curiosity, it's also a cornerstone of modern technology. For example, it's the principle behind the scanning tunneling microscope, a revolutionary tool that allows scientists to see and manipulate individual atoms. By exploiting the tunneling effect, this microscope can create incredibly detailed images of surfaces at the atomic level, opening up new frontiers in materials science and nanotechnology. And then there's the tantalizing possibility of faster-than-light travel. While quantum tunneling doesn't allow particles to actually exceed the speed of light, it does raise intriguing questions about how information might move across barriers instantaneously. Some researchers have explored whether tunneling could be harnessed for ultra-fast communication or even quantum computing, though these ideas remain speculative and face significant challenges. Of course, quantum tunneling also comes with its share of mysteries. For instance, how exactly does a particle decide to tunnel through a barrier, and what happens to it during the tunneling process? These questions push the boundaries of our understanding and remind us that the quantum world is full of surprises. As we wrap up our exploration of quantum tunneling, it's clear that this phenomenon is more than just a quirky quantum trick. It's a fundamental aspect of how the universe operates. From powering stars to enabling cutting-edge technology, quantum tunneling shows us just how strange and wonderful the quantum realm can be. Next, we'll turn our attention to the observer effect, where the very act of looking at a quantum system can change its behavior. Trust me, it's going to get even more fascinating. Now, let's shift our focus to one of the most intriguing and thought-provoking aspects of quantum mechanics, the observer effect. This phenomenon reveals that the very act of observing a quantum system can fundamentally alter its behavior. It's as if the universe knows when we're watching, and it changes its tune accordingly. This idea challenges our everyday intuition, where we assume that observing something doesn't change it. But in the quantum world, the rules are anything but ordinary. To understand the observer effect, we need to revisit one of the most famous experiments in physics, the double-slit experiment. In this setup, particles like electrons or photons are fired at a barrier with two slits. On the other side, a screen records where the particles land. When no one is watching, the particles behave like waves, creating an interference pattern on the screen. This pattern suggests that each particle passes through both slits simultaneously, interfering with itself. But here's where it gets mind-blowing. When scientists place a detector to observe which slit the particle goes through, the interference pattern disappears. The particles suddenly start behaving like discrete objects, passing through one slit or the other. It's as if the act of observation forces the particle to choose a definite path. This experiment raises profound questions about the nature of reality. Does the universe only become definite when we look at it, or is there something deeper at play? The Copenhagen interpretation, one of the foundational theories of quantum mechanics, suggests that the wave function, a mathematical description of a quantum system, collapses into a single state when observed. In other words, observation doesn't just measure reality, it creates it. This idea has sparked endless debates among physicists and philosophers, with some arguing that consciousness itself might play a role in shaping the quantum world. But the observer effect isn't just a philosophical puzzle, it has practical implications too. In quantum computing, for example, the act of measuring a quantum bit or qubit can disturb its state, making it a challenge to extract information without altering the system. This delicate balance between observation and disturbance is a key hurdle in developing reliable quantum technologies. The observer effect also invites us to reconsider our relationship with the universe. If observation can influence reality at the quantum level, what does that mean for our understanding of free will, causality, and the nature of existence itself? While we don't have all the answers, this phenomenon reminds us that the quantum world is far stranger and more interconnected than we ever imagined. As we move forward, we'll explore another fascinating quantum concept, the Quantum Zeno Effect, where frequent observation can seemingly freeze a quantum system in place. It's another twist in the quantum tale that will leave you questioning everything you thought you knew about reality. Now, let's dive into another mind-bending quantum phenomenon, the Quantum Zeno Effect. Named after the ancient Greek philosopher Zeno of Elea, who famously argued that motion is an illusion, this effect suggests that frequent observation can essentially freeze a quantum system in place. It's as if the universe hits the pause button every time we take a peek, preventing the system from evolving naturally. To understand how this works, imagine a quantum particle in a superposition, a state where it exists in multiple possibilities at once. Normally, this particle would evolve over time, transitioning between states. But here's the twist. If you observe the particle repeatedly and quickly enough, it stays locked in its initial state. It's like trying to boil water but constantly checking the temperature. The water never gets a chance to heat up because you're interrupting the process. In the quantum world, this constant observation prevents the system from changing, effectively freezing it in time. This effect isn't just a theoretical curiosity. It has real-world applications, especially in the field of quantum computing. Quantum computers rely on qubits, which can exist in superpositions of states. However, qubits are notoriously fragile, and their states can decay or change due to external influences. By leveraging the Quantum Zeno Effect, scientists can stabilize qubits, keeping them in their desired states for longer periods. This could be a game changer for developing more reliable and powerful quantum technologies. But the Quantum Zeno Effect also raises some fascinating paradoxes. For instance, if observation can halt the evolution of a quantum system, does that mean reality is shaped by how often we look at it? And if so, where do we draw the line between observation and interference? These questions challenge our understanding of causality and the role of the observer in the quantum realm. As we continue to explore the mysteries of quantum mechanics, the Quantum Zeno Effect serves as a reminder of just how strange and counterintuitive this world can be. It's a phenomenon that blurs the line between observation and control, leaving us to wonder whether we're merely spectators or active participants in shaping reality. Next, we'll turn our attention to the quantum gravity conundrum, where we'll explore the challenges of reconciling quantum mechanics with the force that governs the cosmos, gravity. It's a puzzle that has stumped physicists for decades, and one that could hold the key to understanding the very fabric of space-time. Now, let's shift our focus to one of the most perplexing challenges in modern physics, the quantum gravity conundrum. While quantum mechanics has revolutionized our understanding of the microscopic world, and general relativity has given us profound insights into the cosmos, these two pillars of physics seem to clash when it comes to gravity. At their core, they operate under entirely different rules, and bridging this gap has become one of the greatest unsolved problems in science. Quantum mechanics describes the behavior of particles at the smallest scales, where probabilities and uncertainties reign. On the other hand, general relativity, Einstein's masterpiece, explains gravity as the curvature of space-time caused by massive objects. But when we try to apply quantum principles to gravity, things fall apart. Gravity doesn't fit neatly into the quantum framework, and this mismatch becomes glaringly obvious in extreme environments like black holes or the Big Bang, where both quantum effects and gravity are at play. One promising approach to solving this puzzle is loop quantum gravity. This theory suggests that space-time itself might be quantized, meaning it's made up of tiny, discrete loops rather than being smooth and continuous. Imagine space-time as a fabric woven from countless threads, each thread representing a tiny loop. These loops interact and combine to create the structure of the universe as we know it. Loop quantum gravity offers a way to describe gravity in quantum terms, potentially unifying the two frameworks. But while it's an elegant idea, it's still a work in progress, and experimental evidence remains elusive. Another contender in the quest for quantum gravity is string theory, which we touched on earlier. String theory proposes that all particles are vibrations of tiny strings, and it naturally includes gravity as part of its framework. However, string theory requires extra dimensions of space, which complicates things and makes it difficult to test. Despite its mathematical beauty, it hasn't yet provided a definitive answer to the quantum gravity problem. The implications of solving this conundrum are enormous. A successful theory of quantum gravity could explain the nature of spacetime itself, shedding light on the origins of the universe and the inner workings of black holes. It might even reveal whether spacetime is fundamental or emerges from something deeper. But until we find a way to reconcile these two worlds, the quantum gravity conundrum remains a tantalizing mystery, reminding us just how much we still have to learn about the universe. As we move forward, we'll explore another fascinating aspect of quantum reality, the quantum vacuum. This seemingly empty space is anything but, and understanding its secrets could unlock new insights into the forces that shape our universe. Now let's dive into the mysterious realm of the quantum vacuum. At first glance, empty space might seem like just that, empty, but in the quantum world, nothing is ever truly empty. Instead, what we perceive as a void is actually a bubbling, seething sea of virtual particles. These particles pop in and out of existence so quickly that they're almost impossible to detect directly, yet their effects are very real. This phenomenon is rooted in the Heisenberg uncertainty principle, which allows particles to briefly borrow energy from the vacuum, creating pairs of particles and antiparticles that annihilate each other almost instantly. It's like the universe is constantly fizzing with activity, even in the absence of matter. This quantum foam, as it's sometimes called, isn't just a theoretical curiosity, it has measurable consequences. One of the most striking examples is the Casimir effect. When two uncharged metal plates are placed extremely close together in a vacuum, they're pushed toward each other by the pressure of the virtual particles outside the plates. Inside the narrow gap, fewer virtual particles can exist, creating an imbalance that results in a measurable force. This effect has been experimentally confirmed and is a direct demonstration of the quantum vacuum's influence. But the quantum vacuum doesn't just affect tiny objects in a lab. It might hold the key to one of the biggest mysteries in cosmology, dark energy. Observations show that the universe is expanding at an accelerating rate, and scientists believe dark energy is the driving force behind this expansion. One leading hypothesis is that dark energy arises from the energy of the quantum vacuum itself. If this is true, then the seemingly empty space around us is actually filled with an invisible energy that's shaping the fate of the entire cosmos. However, there's a catch. When physicists try to calculate the energy density of the quantum vacuum, they end up with a number that's astronomically larger than what's observed in the universe. This discrepancy, known as the cosmological constant problem, remains one of the biggest unsolved puzzles in physics. It suggests that our understanding of the quantum vacuum is still incomplete, and that there's much more to uncover about this hidden layer of reality. As we peel back the layers of the quantum vacuum, we're reminded that even the emptiest corners of the universe are teeming with activity. From the Casimir effect to the enigma of dark energy, the quantum vacuum challenges our notions of what nothingness really means. And as we continue to explore its secrets, we may find answers to some of the most profound questions about the nature of space, time, and the universe itself. Next, we'll turn our attention to another intriguing idea: the quantum brain hypothesis. Could quantum processes be at work in our own minds, shaping the way we think and perceive the world? Let's find out. Now, let's shift our focus to a theory that bridges the gap between the quantum world and the human mind: the quantum brain hypothesis. This idea suggests that consciousness itself might arise from quantum processes happening within our brains. At first glance, it sounds like something out of science fiction, but there's a growing body of research exploring this fascinating possibility. The quantum brain hypothesis builds on the idea that the brain isn't just a classical computer made of neurons firing in predictable patterns. Instead, it proposes that quantum mechanics plays a crucial role in how we think, perceive, and even make decisions. One of the key figures behind this idea is physicist Roger Penrose, who, along with anesthesiologist Stuart Hameroff, developed the Orchestrated Objective Reduction Theory, or ORCH for short. According to this theory, tiny structures inside neurons called microtubules could act as quantum processors, enabling the brain to perform computations that classical physics alone can't explain. But how could quantum processes even survive in the warm, wet environment of the brain? Critics argue that quantum states are incredibly fragile and would collapse almost instantly under such conditions. However, proponents of the quantum brain hypothesis suggest that the brain's unique structure might protect these delicate quantum states, allowing them to influence neural activity in ways we're only beginning to understand. One of the most intriguing aspects of this theory is its potential to explain the mysterious nature of consciousness. Why do we experience the world the way we do? How does subjective awareness emerge from the physical matter of the brain? If quantum processes are involved, it could mean that consciousness is not just a byproduct of neural activity, but something far more profound, a fundamental feature of the universe itself. Of course, the quantum brain hypothesis is not without its skeptics. Many scientists argue that there's no solid evidence to support the idea that quantum mechanics plays a significant role in brain function. They point out that classical physics and biology can already explain much of what we know about the brain, and introducing quantum mechanics might be unnecessary. Still, the theory continues to spark debate and inspire new research, pushing the boundaries of our understanding of both the mind and the quantum world. As we explore this hypothesis, we're reminded of how much we still have to learn about the brain and consciousness. Whether or not quantum processes are at work in our minds, the quantum brain hypothesis challenges us to think differently about what it means to be conscious and how deeply connected we might be to the quantum fabric of reality. Next, we'll delve into another mind-bending idea: the quantum time hypothesis. Could time itself be quantized, broken into tiny, discrete chunks rather than flowing continuously? Let's find out. Now, let's turn our attention to a theory that challenges one of the most fundamental aspects of our reality: time itself. The quantum time hypothesis proposes that time isn't the smooth, continuous flow we experience in our everyday lives. Instead, it suggests that time is quantized, meaning it's broken into tiny, indivisible chunks, much like how energy is quantized in the quantum world. This idea flips our understanding of time on its head, raising profound questions about the nature of causality and the arrow of time. At the heart of this hypothesis is the idea that time, at its most basic level, operates in discrete steps rather than as an unbroken stream. Think of it like a film reel. What appears to be a seamless motion is actually a series of individual frames. In the same way, the quantum time hypothesis suggests that the flow of time might be made up of incredibly small time quanta, each representing the smallest possible unit of time. These quanta could be so tiny that they're far beyond our ability to perceive, but their existence could fundamentally alter our understanding of how the universe works. One of the most intriguing implications of this theory is its potential impact on the arrow of time, the idea that time moves in one direction from past to future. If time is quantized, it could mean that the arrow of time isn't as straightforward as we think. Some physicists have speculated that at the quantum level, the distinction between past, present, and future might blur, allowing for phenomena that defy our classical understanding of cause and effect. For instance, could events at the quantum level influence each other in ways that seem to reverse the flow of time? It's a mind-bending possibility that challenges our most basic assumptions about reality. The quantum time hypothesis also raises questions about causality. The relationship between cause and effect in a continuous timeline. Causes always precede their effects. But if time is quantized, could there be moments where this order breaks down? Some theories suggest that at the smallest scales, causality might not be as rigid as we imagine, opening the door to scenarios where effects could, in some sense, precede their causes. While this might sound like science fiction, it's a serious area of exploration in theoretical physics, with implications for everything from quantum computing to our understanding of the early universe. Of course, like many quantum theories, the quantum time hypothesis is not without its challenges. One of the biggest hurdles is the lack of experimental evidence. Quantizing time would require detecting these hypothetical time quanta, which is far beyond our current technological capabilities. Additionally, reconciling this idea with our well-established understanding of time in classical physics is no small feat. Critics argue that until there's concrete evidence, the theory remains speculative. Yet, despite these challenges, the quantum time hypothesis continues to captivate scientists and philosophers alike. It pushes us to rethink not just the nature of time, but also how we perceive reality itself. Could time, like space, have a granular structure? And if so, what does that mean for the universe and for us? As we ponder these questions, we're reminded of how much we still have to uncover about the fabric of reality. The quantum time hypothesis invites us to imagine a universe where time itself is built from the tiniest building blocks, challenging us to see the flow of time in a whole new light. Next, we'll explore another fascinating idea, the quantum consciousness theory, and how it suggests that our minds might play a role in shaping the quantum world. Stay tuned. Now, let's shift our focus to one of the most provocative ideas in quantum physics, the quantum consciousness theory. This theory suggests that consciousness itself might play a role in shaping the quantum world, blurring the line between the observer and the observed. It's a concept that has sparked heated debates among scientists and philosophers, challenging our understanding of both the mind and the universe. At its core, the quantum consciousness theory proposes that the act of observation, or more specifically, consciousness, can influence the behavior of quantum systems. This idea builds on the famous double-slit experiment, where particles like electrons behave differently when observed. In the quantum world, particles exist in a state of superposition, meaning they can be in multiple states at once until they're measured. But what if it's not just the act of measurement that collapses these states? What if consciousness itself is the key? Some proponents of this theory argue that consciousness isn't just a passive observer but an active participant in the quantum realm. They suggest that the mind has the power to influence the outcome of quantum events, effectively shaping reality at its most fundamental level. This idea has led to fascinating experiments, such as those exploring whether human intention can affect random quantum processes. While the results are still debated, these studies have opened up new avenues for exploring the relationship between mind and matter. One of the most intriguing aspects of the quantum consciousness theory is its philosophical implications. If consciousness can influence quantum states, does that mean our thoughts and intentions have a tangible impact on the physical world? Could this explain phenomena like intuition or even the placebo effect? These questions push us to reconsider the nature of reality and our place within it. However, critics argue that the theory lacks a solid scientific foundation and risks veering into pseudoscience. They point out that consciousness is still poorly understood, and linking it to quantum mechanics without clear evidence is speculative at best. Despite the controversy, the quantum consciousness theory continues to captivate researchers and thinkers. It challenges us to explore the boundaries of science and philosophy, asking whether the mind and the universe are more deeply connected than we realize. Could consciousness be a fundamental aspect of reality, woven into the very fabric of the quantum world, or is this theory a step too far into the realm of speculation? As we grapple with these questions, we're reminded of how much we still have to learn about the mysteries of existence. Next, we'll dive into another fascinating concept, the quantum Darwinism theory, and how it explains the emergence of classical reality from the quantum realm. Stay with us as we continue to unravel the secrets of the universe. Now, let's turn our attention to a theory that offers a fresh perspective on how the quantum world transitions into the classical reality we experience every day: the quantum Darwinism theory. This idea suggests that certain quantum states survive and become dominant through their interactions with the environment, effectively explaining why we perceive a stable, classical world rather than a chaotic quantum one. At its heart, quantum Darwinism proposes that the environment acts as a kind of filter, selecting which quantum states are most likely to persist. Imagine a quantum system like a particle in superposition, existing in multiple states at once. As this system interacts with its surroundings, whether it's air molecules, light, or other particles, some of these states become more visible to the environment. These states are then copied and spread throughout the environment, making them more likely to be observed. In a sense, the environment chooses which quantum states survive, and these selected states are what we perceive as classical reality. This process is often compared to natural selection in biology, where only the fittest organisms survive and reproduce. In quantum Darwinism, the fittest quantum states are the ones that can be most easily copied and shared with the environment. Over time, these states become the dominant ones, giving rise to the stable, predictable world we're familiar with. It's a fascinating way to bridge the gap between the strange, probabilistic nature of quantum mechanics and the seemingly solid, deterministic world of classical physics. One of the key implications of quantum Darwinism is that it helps solve the so-called measurement problem in quantum mechanics. This problem arises because quantum systems seem to behave differently when observed, leading to questions about how and why the act of measurement collapses a quantum state into a single outcome. Quantum Darwinism suggests that the environment itself acts as a continuous observer, constantly interacting with quantum systems and selecting the states that become classical. This means that the collapse of the wave function isn't a mysterious event triggered by human observation, but a natural consequence of the system's interaction with its surroundings. Critics of quantum Darwinism argue that while it provides an elegant explanation, it still leaves some questions unanswered. For example, how exactly does the environment select certain states over others? And can this theory fully account for the complexity of quantum systems in real-world scenarios? Despite these challenges, quantum Darwinism has gained traction as a promising framework for understanding the transition from quantum to classical reality. As we reflect on this theory, it's worth considering how it reshapes our understanding of the universe. If quantum Darwinism is correct, then the classical world we see around us isn't just a random outcome, it's the result of a natural selection process at the quantum level. This idea not only deepens our appreciation for the complexity of the quantum realm, but also highlights the intricate interplay between systems and their environments. Next, we'll explore another intriguing concept, the quantum decoherence theory, and how it complements quantum Darwinism in explaining the emergence of classical reality. Stay tuned as we continue to unravel the mysteries of the quantum world. Now, shifting our focus to another pivotal concept, let's dive into the quantum decoherence theory. This theory offers a compelling explanation for how the strange, probabilistic nature of quantum systems gives way to the familiar, classical world we observe. At its core, quantum decoherence describes the process by which a quantum system loses its coherence, its ability to exist in multiple states simultaneously due to interactions with its environment. This loss of coherence is what makes quantum systems appear to collapse into a single classical state. To understand this better, let's revisit the idea of superposition, where a quantum particle can exist in multiple states at once. For example, an electron can be in two places simultaneously or spin in opposite directions at the same time. However, when this particle interacts with its surroundings, whether it's photons, air molecules, or other particles, it begins to leak information about its state into the environment. This interaction causes the quantum system to become entangled with its surroundings, effectively spreading its superposition across a much larger system. As a result, the original quantum state loses its coherence, and the system appears to settle into a single, classical state. This process is crucial for understanding the measurement problem in quantum mechanics. Why does a quantum system seem to choose a single state when observed? Quantum decoherence suggests that it's not the act of observation itself that causes the collapse, but rather the system's inevitable interaction with its environment. In other words, the environment acts as a kind of witness, constantly interacting with the quantum system and causing it to decohere. This means that the classical reality we perceive is not a result of some mysterious collapse, but a natural outcome of the system's entanglement with its surroundings. One of the most fascinating aspects of quantum decoherence is its implications for quantum computing. In a quantum computer, information is stored in qubits, which rely on maintaining superposition and entanglement to perform complex calculations. However, decoherence poses a significant challenge because it causes qubits to lose their quantum properties, leading to errors in computation. To build practical quantum computers, scientists must find ways to minimize decoherence, often by isolating qubits from their environment or using error-correcting codes. This ongoing battle against decoherence highlights just how delicate and intricate quantum systems truly are. Critics of quantum decoherence argue that while it explains how quantum systems appear classical, it doesn't fully resolve the measurement problem. For instance, it doesn't explain why a particular classical state is chosen over others. However, when combined with theories like quantum Darwinism, decoherence provides a more complete picture of how the quantum world transitions into the classical one. Together, these theories suggest that the environment not only causes decoherence but also selects which states become dominant, shaping the reality we observe. As we reflect on quantum decoherence, it's clear that this theory plays a vital role in bridging the gap between the quantum and classical realms. It not only deepens our understanding of the measurement problem, but also underscores the challenges and opportunities in fields like quantum computing. By exploring how quantum systems lose coherence, we gain valuable insights into the fundamental nature of reality itself. Next, we'll turn our attention to the quantum field theory, a framework that describes particles as excitations of underlying fields. Stay with us as we continue to unravel the mysteries of the quantum universe. Now, stepping into the realm of quantum field theory, we encounter a framework that redefines how we perceive the building blocks of the universe. Unlike traditional particle physics, which treats particles as discrete entities, quantum field theory paints a picture where particles are merely excitations, tiny ripples, in underlying fields that permeate all of space and time. Imagine the universe as a vast ocean and particles as waves on its surface. These fields are not just abstract concepts but the very fabric of reality, each corresponding to a fundamental force or particle, such as the electromagnetic field or the Higgs field. One of the most remarkable achievements of quantum field theory is its ability to unify three of the four fundamental forces of nature: electromagnetism, the weak nuclear force, and the strong nuclear force. This unification is achieved through the concept of gauge symmetry, which describes how fields interact and transform under certain conditions. For instance, the electromagnetic force is mediated by photons, which are excitations of the electromagnetic field. Similarly, the weak nuclear force is carried by W and Z bosons, while the strong nuclear force is governed by gluons. Quantum field theory provides a mathematical framework that elegantly describes these interactions, offering a deeper understanding of how the universe operates at its most fundamental level. However, despite its successes, quantum field theory faces significant challenges, particularly when it comes to gravity. While it beautifully explains the other three forces, gravity remains stubbornly resistant to being incorporated into this framework. General relativity, Einstein's theory of gravity, describes it as the curvature of space-time, a concept that doesn't neatly fit into the quantum field picture. This disconnect has led to one of the greatest unsolved problems in physics: the quest for a theory of quantum gravity that can reconcile these two seemingly incompatible descriptions of reality. Another challenge lies in the mathematical complexity of quantum field theory itself. Calculations often involve infinite quantities, requiring sophisticated techniques like renormalization to produce meaningful results. While these methods have been incredibly successful, leading to predictions that match experimental observations with astonishing precision, they also highlight the limitations of our current understanding. Some physicists argue that these infinities point to a deeper, more fundamental theory that we have yet to discover. Yet, for all its challenges, quantum field theory remains one of the most powerful tools in modern physics. It has not only provided a framework for understanding particle interactions, but also led to groundbreaking discoveries, such as the prediction and eventual detection of the Higgs boson. This particle, an excitation of the Higgs field, is responsible for giving other particles their mass, a cornerstone of the standard model of particle physics. Without quantum field theory, such insights would remain beyond our grasp. As we explore this theory, it's clear that quantum field theory is more than just a mathematical construct. It's a lens through which we can glimpse the underlying structure of the universe. While it doesn't yet provide all the answers, it continues to guide us toward a deeper understanding of the forces that shape our reality. Next, we'll delve into quantum information theory, where we'll uncover how information itself might be the fundamental currency of the cosmos. Stay tuned as we continue our journey through the quantum mysteries of the universe. Now, shifting our focus to the intriguing world of quantum information theory, we uncover a perspective that redefines our understanding of the universe itself. At its core, this theory proposes that information is not just a byproduct of physical processes, it is the very foundation of reality. Imagine the universe as a vast, intricate network of data, where every particle, every interaction, and every event encodes information. This idea challenges our traditional view of physics, suggesting that the cosmos operates more like a quantum computer than a collection of inert matter. One of the most fascinating aspects of quantum information theory is its connection to black holes and the infamous information paradox. According to classical physics, when matter falls into a black hole, it is lost forever, taking all its information with it. But quantum mechanics tells us that information cannot be destroyed, it must be preserved. This contradiction, known as the black hole information paradox, has puzzled physicists for decades. Quantum information theory offers a potential solution by suggesting that the information swallowed by a black hole isn't truly lost. Instead, it might be encoded on the black hole's event horizon, the boundary beyond which nothing can escape. This idea aligns with the holographic principle, which posits that all the information contained within a volume of space can be represented as a hologram on its boundary. In other words, our three-dimensional universe might be a projection of information stored on a two-dimensional surface. The holographic principle has profound implications for our understanding of reality. It suggests that the universe operates like a cosmic hard drive, with every bit of information meticulously stored and processed. This perspective bridges the gap between quantum mechanics and gravity, offering a potential pathway toward a unified theory of everything. It also raises mind-bending questions about the nature of space and time. Could space-time itself be an emergent property of quantum information? And if so, what does that mean for our perception of reality? Quantum information theory also plays a crucial role in the development of quantum computing. By treating information as a fundamental entity, researchers are exploring ways to harness the power of quantum systems to perform calculations far beyond the reach of classical computers. This could revolutionize fields like cryptography, materials science, and artificial intelligence, opening up new frontiers in technology and discovery. As we explore this theory, it becomes clear that information is not just a tool for communication or computation, it is the very fabric of the universe. From the enigmatic depths of black holes to the cutting-edge world of quantum computing, quantum information theory offers a fresh lens through which to view the cosmos. Next, we'll dive into the concept of quantum supremacy, where we'll explore how quantum computers are poised to outperform their classical counterparts. Stay with us as we continue unraveling the mysteries of the quantum realm. Now, let's step into the fascinating realm of quantum supremacy, a concept that marks a turning point in the evolution of computing. Quantum supremacy refers to the moment when a quantum computer can solve a problem that is practically impossible for even the most powerful classical computers to tackle. This isn't just about speed, it's about fundamentally redefining what's possible in computation. The journey toward quantum supremacy began with the realization that quantum systems, with their ability to exist in multiple states simultaneously, could process information in ways that classical systems simply cannot. In 2019, Google's quantum processor, Sycamore, made headlines by achieving this milestone. It solved a specific problem in just 200 seconds, a task that would have taken the world's fastest supercomputer thousands of years to complete. This breakthrough wasn't just a technical feat. It was a glimpse into a future where quantum computers could revolutionize industries, from drug discovery to climate modeling. But what makes quantum computers so powerful? The answer lies in qubits, the quantum equivalent of classical bits. Unlike classical bits, which can only be in a state of 0 or 1, qubits can exist in a superposition of both states at once. This allows quantum computers to explore countless possibilities simultaneously, making them exceptionally well-suited for solving complex optimization problems, simulating molecular structures, and cracking encryption codes that are currently unbreakable. However, achieving quantum supremacy is just the beginning. The real challenge lies in building practical, scalable quantum computers that can handle real-world applications. Current quantum systems are highly sensitive to external disturbances, requiring extreme conditions like near-absolute zero temperatures to function. Researchers are also working on error correction techniques to address the inherent instability of qubits. Despite these hurdles, the progress has been remarkable, with companies and governments investing billions into quantum research. Looking ahead, the potential of quantum supremacy is staggering. Imagine a world where we can design new materials with unprecedented properties, optimize global supply chains in real time, or even simulate the behavior of entire ecosystems to combat climate change. Quantum computers could also unlock new frontiers in artificial intelligence, enabling machines to learn and adapt in ways that are currently unimaginable. Yet with great power comes great responsibility. The ability of quantum computers to break traditional encryption methods raises significant concerns about cybersecurity. This has spurred a race to develop quantum-resistant encryption, ensuring that our digital infrastructure remains secure in the quantum age. As we stand on the brink of this technological revolution, quantum supremacy challenges us to rethink the limits of computation and innovation. It's not just about building faster machines, it's about unlocking new possibilities that could reshape our understanding of science, technology, and the universe itself. Next, we'll explore the intriguing concept of quantum teleportation, where information transcends the boundaries of space and time. Stay tuned as we continue our journey through the quantum frontier. Now, let's shift our focus to one of the most mind-bending concepts in quantum physics: quantum teleportation. No, this isn't about beaming people across the galaxy like in science fiction. It's about transmitting information instantaneously using the strange phenomenon of quantum entanglement. Imagine being able to send data from one point to another without it physically traveling through space. Sounds impossible, right? Well, in the quantum world, it's not only possible, it's already happening. Quantum teleportation relies on the principle of entanglement, where two particles become so deeply connected that the state of one instantly influences the state of the other, no matter how far apart they are. This connection defies our classical understanding of space and time, earning it the nickname spooky action at a distance. Here's how it works. If you entangle two particles and then measure the state of one, the other particle's state will instantly match it, even if it's on the other side of the universe. This instantaneous link is the foundation of quantum teleportation. But how does this translate to transmitting information? Let's break it down. Suppose you have two entangled particles. Let's call them particle A and particle B. Particle A stays with you while particle B is sent to a distant location. Now, if you want to teleport information, you combine particle A with a third particle that carries the data you want to send. By performing a specific measurement on particle A and the data-carrying particle, you can instantly alter the state of particle B to match the information you're trying to transmit. The result, the information appears at the distant location without ever physically traveling there. This process has already been demonstrated in laboratories, with scientists successfully teleporting quantum states over distances of hundreds of kilometers. The implications are enormous. Quantum teleportation could revolutionize secure communication, enabling the creation of unhackable quantum networks. It could also play a crucial role in the development of quantum internet, where data is transmitted with unprecedented speed and security. However, there are significant limitations to this technology. For one, quantum teleportation requires a classical communication channel to send additional information about the measurement performed on particle A. This means that while the quantum state is transmitted instantaneously, the process as a whole isn't faster than the speed of light. Additionally, maintaining entanglement over long distances is incredibly challenging, as particles are easily disrupted by their environment. This makes scaling up quantum teleportation for practical applications a daunting task. Despite these challenges, the potential of quantum teleportation is undeniable. It opens up possibilities for secure communication, advanced quantum computing, and even new ways to explore the fundamental nature of reality. As we continue to push the boundaries of quantum science, who knows what other astonishing discoveries await. Next, we'll dive into the unpredictable world of quantum chaos theory, where order and randomness collide in the quantum realm. Stay tuned as we unravel the mysteries of this fascinating phenomenon. Now, let's step into the wild and unpredictable world of quantum chaos theory. If you thought quantum mechanics was already strange, this theory takes things to a whole new level. Quantum chaos theory explores how even the tiniest particles can behave in ways that seem completely random and unpredictable, challenging our ideas about order and determinism in the universe. At first glance, chaos might seem like the opposite of what science is all about. After all, science seeks to explain and predict how things work. But in the quantum realm, chaos isn't just a lack of order, it's a fundamental feature of how particles interact. Imagine trying to predict the exact path of a single electron as it moves through space. In classical physics, you might expect it to follow a predictable trajectory, like a ball rolling down a hill. But in quantum mechanics, the electron's behavior is far more erratic. It might appear in one place, vanish, and then reappear somewhere entirely different, as if it's dancing to its own mysterious rhythm. This unpredictability is at the heart of quantum chaos theory. It shows us that even in systems governed by precise laws, tiny changes in initial conditions can lead to wildly different outcomes. This idea is often referred to as the butterfly effect in classical chaos theory, where a butterfly flapping its wings in one part of the world could theoretically influence the weather on the other side of the globe. In the quantum world, this sensitivity to initial conditions is even more pronounced, making it nearly impossible to predict the exact state of a system over time. But why does this matter? For one, it challenges the idea of determinism, the belief that every event is caused by preceding events, and that if we knew all the initial conditions, we could predict the future with absolute certainty. Quantum chaos theory suggests that at the smallest scales, the universe is inherently unpredictable. This doesn't mean that everything is random, but rather that there's a fundamental limit to how much we can know and predict about quantum systems. This has profound implications for fields like quantum computing and cryptography. In quantum computing, for example, the chaotic behavior of particles can make it difficult to maintain stability and control over qubits, the building blocks of quantum information. On the flip side, this same unpredictability can also be harnessed to create ultra-secure encryption methods, where the chaotic nature of quantum systems makes it nearly impossible for hackers to crack the code. Quantum chaos theory also raises fascinating questions about the nature of reality itself. If the universe is governed by laws that allow for such unpredictability, what does that say about free will, causality, and the very fabric of existence? While we don't have all the answers yet, exploring these questions pushes the boundaries of our understanding and opens up new avenues for discovery. As we continue to unravel the mysteries of quantum chaos, one thing is clear: the quantum realm is far more complex and unpredictable than we ever imagined. And with each new insight, we're reminded that the universe is full of surprises waiting to be uncovered. Up next, we'll explore how quantum mechanics applies to the entire cosmos in quantum cosmology theory, where the Big Bang and the origins of spacetime take center stage. Stay tuned, this is where the quantum meets the cosmic. Now, let's zoom out from the chaotic dance of particles and take a cosmic perspective with quantum cosmology theory. This theory takes the strange and counterintuitive rules of quantum mechanics and applies them to the entire universe, offering a fresh lens through which to view the origins and evolution of everything we know. At its core, quantum cosmology theory seeks to answer one of the most profound questions in science. How did the universe begin, and what role did quantum mechanics play in its birth? To understand this, we need to rewind the clock to the very beginning, the Big Bang. According to the standard model of cosmology, the universe started as an unimaginably hot and dense point, smaller than an atom. But here's where quantum mechanics comes into play. At such tiny scales, the rules of classical physics break down and quantum effects dominate. This means that the early universe wasn't just a smooth, uniform expansion. It was a seething, fluctuating quantum soup where particles and energy flickered in and out of existence. One of the key ideas in quantum cosmology theory is that these quantum fluctuations didn't just disappear as the universe expanded. Instead, they left an imprint on the fabric of space-time itself. Over billions of years, these tiny ripples grew into the vast cosmic structures we see today: galaxies, stars, and even the cosmic web that connects everything. In a sense, the universe we inhabit is the result of quantum randomness writ large, a cosmic tapestry woven from the threads of quantum uncertainty. But the story doesn't end there. Quantum cosmology theory also delves into the concept of inflation, a rapid expansion of the universe that occurred just fractions of a second after the Big Bang. During this period, the universe grew exponentially, stretching quantum fluctuations across vast distances. This process not only explains why the universe appears so uniform on large scales, but also provides a mechanism for the formation of galaxies and other structures. Without inflation, the universe as we know it might never have come into existence. What's truly mind-bending is the idea that spacetime itself may have quantum origins. Some theories suggest that spacetime isn't a smooth, continuous fabric, but is instead made up of discrete, quantized units, tiny building blocks that form the foundation of reality. This idea challenges our classical understanding of space and time, suggesting that even the most fundamental aspects of the universe are governed by quantum rules. So, what does all this mean for our understanding of the cosmos? Quantum cosmology theory bridges the gap between the very small and the very large, showing how the bizarre behavior of particles at the quantum scale can shape the entire universe. It reminds us that the cosmos isn't just a collection of stars and galaxies, it's a dynamic, evolving system with deep connections to the quantum realm. As we continue to explore these ideas, we're left with more questions than answers. How did the quantum fluctuations of the early universe give rise to the complexity we see today? What does it mean for spacetime to have quantum origins, and could there be other universes born from different quantum fluctuations existing alongside our own? These are the kinds of questions that quantum cosmology theory invites us to ponder, pushing the boundaries of our understanding and opening up new frontiers in science. Next up, we'll dive into the fascinating world of quantum biology theory, where we'll explore how quantum processes might be at work in living organisms, from photosynthesis to bird navigation. Get ready to see the quantum world in a whole new light. This is where science meets life itself. Now, let's shift our focus from the vast cosmos to the intricate world of life itself with quantum biology theory. This fascinating idea suggests that the strange and counterintuitive rules of quantum mechanics don't just apply to particles in a lab. They might also be at work inside living organisms. From the way plants harness sunlight to how birds navigate across continents, quantum processes could be playing a hidden role in the very fabric of life. Let's start with photosynthesis, the process by which plants convert sunlight into energy. At first glance, this might seem like a straightforward chemical reaction, but dig a little deeper and you'll find something extraordinary. Scientists have discovered that the energy from sunlight doesn't just travel in a straight line through a plant's cells. Instead, it takes advantage of a quantum phenomenon called coherence. This means the energy can explore multiple pathways simultaneously, almost as if it's testing all possible routes before settling on the most efficient one. It's like nature has its own built-in quantum computer, optimizing energy transfer in ways that classical physics can't fully explain. But plants aren't the only ones tapping into the quantum realm. Birds, particularly migratory species, have long puzzled scientists with their incredible ability to navigate across thousands of miles with pinpoint accuracy. The secret might lie in a quantum process involving a protein in their eyes called cryptochrome. This protein is sensitive to Earth's magnetic field, and some researchers believe it uses quantum entanglement, a phenomenon where particles remain connected across vast distances, to act as a biological compass. In other words, birds might be using quantum mechanics to see the Earth's magnetic field, guiding them on their epic journeys. And then there's the world of enzymes, the molecular machines that drive countless chemical reactions in our bodies. Enzymes are incredibly efficient, often speeding up reactions by factors of millions. But how do they achieve such precision? Some scientists think quantum tunneling might be the key. This is the idea that particles can tunnel through barriers that would be impossible to cross under classical physics. In enzymes, this could allow protons or electrons to jump between molecules in ways that defy traditional chemistry, making life's essential processes faster and more efficient. So, what does all this mean? Quantum biology theory challenges the traditional view that life operates solely on the rules of classical physics. Instead, it suggests that the quantum world and the biological world are deeply intertwined, with quantum effects playing a subtle but crucial role in the processes that keep us alive. It's a reminder that the boundary between the quantum and the classical isn't as clear-cut as we once thought, and that life itself might be one of the most complex quantum systems of all. As we continue to explore this emerging field, we're left with even more questions. How widespread are these quantum effects in biology? Could they explain other mysteries of life, like consciousness or the origins of life itself? And what might this mean for the future of medicine or technology? Quantum biology theory opens up a whole new frontier of discovery, where the quantum and the living collide in ways we're only beginning to understand. Next, we'll turn our attention to quantum entropy theory, where we'll explore how the concept of entropy, the measure of disorder, plays out in the quantum realm, shaping everything from black holes to the arrow of time. Get ready to dive into the chaotic yet fascinating world of quantum disorder. Now, let's venture into the intriguing world of quantum entropy theory, where the concept of disorder takes on a whole new dimension. Entropy, often described as the measure of chaos or randomness in a system, is a cornerstone of classical physics, but in the quantum realm it becomes even more fascinating and a bit more mysterious. So, how does entropy work when we zoom in to the level of particles and probabilities? And what does it mean for the universe as a whole? To start, let's revisit the basics. In classical physics, entropy is tied to the second law of thermodynamics, which states that in any closed system, disorder tends to increase over time. Think of it like a messy room. It's easier for things to become disorganized than to stay neat. But in quantum systems, entropy isn't just about disorder, it's also about information. Every particle, every interaction carries with it a kind of quantum information, and entropy measures how much of that information is lost or scrambled as a system evolves. One of the most dramatic places to see quantum entropy in action is inside black holes. These cosmic giants are famous for their immense gravitational pull, but they're also laboratories for some of the most extreme physics in the universe. When matter falls into a black hole, it doesn't just disappear, it leaves behind a kind of quantum footprint. This is where entropy comes into play. According to Stephen Hawking's groundbreaking work, black holes have entropy, and it's directly related to the surface area of their event horizons, the point of no return. The larger the black hole, the higher its entropy, and the more information it effectively hides from the rest of the universe. This connection between entropy and black holes has led to some of the most profound questions in physics, like the famous black hole information paradox. If information can't be destroyed, where does it go when it enters a black hole? But quantum entropy doesn't just shape the cosmos, it also shapes time itself. The arrow of time, the idea that time moves forward in one direction, is deeply tied to entropy. In the quantum world, entropy helps explain why certain processes are irreversible. For example, when a cup of coffee cools down, it's because heat, a form of energy, spreads out into the surrounding environment, increasing entropy. In quantum terms, this means the system evolves from a state of lower entropy to higher entropy, and there's no going back. This irreversible flow is what gives time its direction, making the past distinct from the future. So, what does all this mean for our understanding of the universe? Quantum entropy theory suggests that entropy isn't just a measure of disorder. It's a fundamental part of how the universe stores and processes information. From the depths of black holes to the flow of time itself, entropy is a key player in shaping the cosmos. It's a reminder that even in the quantum realm, where particles can exist in multiple states at once, there's an underlying order to the chaos. As we continue to explore this theory, we're left with even more questions. How does quantum entropy influence the evolution of the universe on the largest scales? Could it hold the key to unifying quantum mechanics and gravity? And what might it tell us about the ultimate fate of the cosmos? Quantum entropy theory opens up a world of possibilities, where the interplay of disorder and information reveals the hidden structure of reality. Next, we'll dive into quantum duality theory, where we'll explore the strange and fascinating idea that particles can behave as both waves and particles, depending on how we observe them. Get ready to unravel one of the most mind-bending mysteries of quantum mechanics. Now, let's shift our focus to one of the most iconic and puzzling aspects of quantum mechanics, quantum duality theory. This theory reveals a fundamental truth about the nature of reality. Particles, like electrons and photons, don't behave like the solid, predictable objects we're used to in the everyday world. Instead, they can act as both particles and waves depending on how we observe them. This duality lies at the heart of quantum mechanics and challenges our very understanding of what it means to be something. To grasp this concept, let's start with a classic experiment, the double-slit experiment. Imagine shining a beam of light through two narrow slits onto a screen. If light were purely a particle, you'd expect to see two distinct bands of light on the screen corresponding to the slits. But what actually happens is far stranger. Instead of two bands, you see an interference pattern, a series of light and dark bands that look like ripples on water. This pattern suggests that light behaves like a wave, spreading out and interfering with itself as it passes through the slits. But here's the twist: if you try to measure which slit the light passes through, the interference pattern disappears and the light behaves like a particle again. It's as if the act of observation forces the light to choose between being a wave or a particle. This strange behavior isn't limited to light. Electrons, which we typically think of as tiny particles, also exhibit wave-like properties. In fact, the double-slit experiment works just as well with electrons, producing the same interference pattern. This duality isn't just a quirk of the experiment, it's a fundamental property of quantum objects. They exist in a kind of superposition where they're neither purely particles nor purely waves until we measure them. This raises profound questions about the nature of reality. Is the universe inherently uncertain, or does our observation somehow shape the world around us? The implications of wave-particle duality go far beyond the lab. It challenges the very idea of an objective reality, suggesting that what we perceive as real might depend on how we interact with it. For example, in quantum computing, this duality is harnessed to perform calculations that would be impossible for classical computers. By exploiting the wave-like properties of particles, quantum computers can explore multiple possibilities simultaneously, opening up new frontiers in technology and science. But the mystery doesn't end there. Wave-particle duality also forces us to rethink the nature of measurement itself. In classical physics, measurement is a straightforward process. You observe something and it stays the same. But in the quantum world, measurement is an active process that changes the system being observed. This is known as the observer effect, and it's a direct consequence of wave-particle duality. Every time we measure a quantum system, we're not just passively observing it, we're influencing it, collapsing its wave function into a definite state. This blurring of the line between observer and observed is one of the most profound insights of quantum mechanics. So, what does all this mean for our understanding of reality? Quantum duality theory suggests that the universe is far more fluid and interconnected than we ever imagined. Particles and waves aren't separate entities, they're two sides of the same coin, revealing different aspects of the same underlying reality. This duality reminds us that the quantum world operates on principles that defy our everyday intuition. inviting us to rethink what we know about the nature of existence. As we continue to explore this theory, we're left with even more questions. How does wave-particle duality shape the behavior of larger objects? Could it hold the key to understanding the boundary between the quantum and classical worlds? And what might it tell us about the ultimate nature of reality? Quantum duality theory invites us to embrace the mystery, challenging us to see the universe not as a collection of fixed objects, but as a dynamic interplay of possibilities. Next, we'll delve into quantum non-locality theory, where we'll explore the mind-bending idea that particles can influence each other instantaneously, no matter how far apart they are. Get ready to question everything you thought you knew about space and time. Now, let's step into one of the most mind-bending corners of quantum mechanics, quantum non-locality theory. This theory takes the strangeness of quantum behavior to a whole new level, suggesting that particles can influence each other instantaneously, no matter how far apart they are. It's a concept that defies our everyday understanding of space and time, challenging the very foundations of classical physics. To understand non-locality, let's revisit the idea of quantum entanglement. Imagine two particles that are entangled, meaning their properties are deeply connected. If you measure one particle, the other instantly knows the result, even if it's light years away. This connection happens faster than the speed of light, which, according to Einstein's theory of relativity, should be impossible. Einstein famously called this spooky action at a distance, and it's a phrase that perfectly captures the eerie nature of this phenomenon. But how does this work? In classical physics, information can't travel faster than light. Yet, in the quantum world, entangled particles seem to communicate instantaneously. This isn't just a theoretical idea, it's been proven through experiments. One of the most famous is the Bell test, which confirmed that entangled particles really do share this mysterious connection. The results of these experiments have profound implications. They suggest that the universe is far more interconnected than we ever imagined, with particles sharing a kind of hidden link that transcends space and time. This idea of non-locality doesn't just challenge classical physics, it turns it on its head. In the classical view, the universe is made up of separate, independent objects that interact through forces like gravity or electromagnetism. But quantum non-locality suggests that everything is deeply connected, with particles influencing each other in ways that don't depend on distance. This raises big questions about the nature of reality. Is the universe fundamentally one interconnected whole? And if so, what does that mean for our understanding of space, time, and causality? One of the most intriguing aspects of non-locality is its potential to revolutionize communication and technology. If we could harness this instantaneous connection, it could lead to breakthroughs in quantum communication, allowing us to send information faster than ever before. But there's a catch. While entangled particles can influence each other instantly, we can't use this connection to send messages faster than light. The reason is that the results of measurements on entangled particles are random until they're observed. So, while the connection is instantaneous, it's also unpredictable, making it impossible to use for traditional communication. Despite this limitation, quantum non-locality continues to inspire scientists and philosophers alike. It challenges us to rethink our assumptions about the universe and pushes the boundaries of what we consider possible. Could this interconnectedness extend beyond particles to larger objects or even to us? Some theories suggest that non-locality might play a role in consciousness or the fabric of reality itself, though these ideas remain speculative. As we grapple with the implications of quantum non-locality theory, we're left with more questions than answers. How does this instantaneous connection work? What does it tell us about the nature of space and time? And could it hold the key to unlocking even deeper mysteries of the universe? Non-locality reminds us that the quantum world is full of surprises. inviting us to explore a reality that's far stranger and more interconnected than we ever imagined. Next, we'll explore quantum reality collapse theory, where we'll dive into the idea that reality itself collapses into a single state when observed. Get ready to question everything you thought you knew about existence. Now, let's venture into one of the most perplexing ideas in quantum mechanics: quantum reality collapse theory. This theory takes the act of observation and turns it into something far more profound, suggesting that reality itself doesn't exist in a definite state until we look at it. It's a concept that blurs the line between the observer and the observed, challenging our most basic assumptions about existence. To understand this, let's revisit the famous double-slit experiment. When particles like electrons are fired at a barrier with two slits, they create an interference pattern on the other side, behaving like waves. But here's the twist. If you try to observe which slit the electron goes through, the interference pattern disappears and the electrons start behaving like particles. It's as if the act of looking forces the electron to choose a definite state. This phenomenon is at the heart of quantum reality collapse theory, which proposes that observation plays a crucial role in shaping reality. But what does this really mean? In the quantum world, particles exist in a superposition of all possible states until they're observed. Think of it like a coin spinning in the air. It's neither heads nor tails until it lands. Similarly, a quantum particle doesn't decide its position or momentum until it's measured. This idea was central to the Copenhagen interpretation, one of the earliest and most influential frameworks in quantum mechanics. According to this view, the wave function, a mathematical description of a quantum system, collapses into a single state when observed, bringing reality into focus. This raises some profound questions. If observation is what collapses the wave function, what counts as an observer? Is it a human, a machine, or something else entirely? And what happens when no one is looking? Some interpretations suggest that the universe remains in a fuzzy, undefined state until consciousness interacts with it. Others argue that the collapse happens through interactions with the environment, even without a conscious observer. These debates highlight the deep philosophical implications of quantum reality collapse theory, forcing us to reconsider the nature of reality itself. From a scientific perspective, this theory has far-reaching consequences. It challenges the idea of an objective reality, suggesting that the universe is fundamentally participatory. In other words, reality isn't something that exists independently of us. It's something we help create through observation. This idea has inspired countless experiments, from testing the limits of superposition to exploring the role of consciousness in quantum systems. While the results are still debated, they continue to push the boundaries of our understanding. One of the most intriguing aspects of this theory is its connection to the concept of quantum decoherence. Decoherence explains how quantum systems lose their superposition and appear classical when they interact with their surroundings. It's like the spinning coin finally landing due to air resistance. While decoherence provides a mechanism for how superpositions collapse, it doesn't fully explain why observation plays such a critical role. This leaves room for ongoing exploration and debate, keeping quantum reality collapse theory at the forefront of quantum research. As we reflect on this theory, we're left with more questions than answers. Does reality truly depend on observation? If so, what does that mean for our place in the universe? And could this idea hold the key to understanding the deeper mysteries of existence? Quantum reality collapse theory invites us to rethink everything we thought we knew about reality, reminding us that the quantum world is as mysterious as it is fascinating. Next, we'll wrap up our journey through these 30 mind-bending theories, exploring how they collectively challenge and expand our understanding of the universe. Get ready to see the bigger picture. As we bring this exploration to a close, let's take a moment to reflect on the incredible journey we've taken through these 30 groundbreaking theories about the universe's quantum realities. From the mind-bending many worlds interpretation to the mysterious quantum reality collapse theory, each idea has pushed the boundaries of our understanding, challenging us to rethink the very fabric of existence. These theories don't just offer answers, they open doors to new questions, inviting us to explore the unknown and embrace the wonder of the cosmos. What's truly remarkable is how these theories, though distinct, weave together to paint a larger picture of the universe. They remind us that reality is far stranger and more complex than we ever imagined. Whether it's the idea of infinite parallel universes, the notion that particles can be entangled across vast distances, or the possibility that our universe is a hologram, each theory adds a unique piece to the puzzle. Together, they challenge the notion of a static, predictable universe, revealing instead a dynamic, interconnected reality shaped by the principles of quantum mechanics. But perhaps the most profound takeaway is how these theories force us to confront our role in the cosmos. Are we mere observers, or do we play an active part in shaping reality? Do our choices ripple across infinite universes, or is our existence confined to a single, fleeting moment in time? These questions don't just belong to physicists, they belong to all of us, inviting us to ponder our place in the grand tapestry of existence. As we wrap up, I want to leave you with a question to ponder. If the universe is as mysterious and interconnected as these theories suggest, what does that mean for the future of science and for humanity itself? Could unlocking the secrets of quantum reality lead to breakthroughs that transform our understanding of life, technology, and even consciousness? The possibilities are as vast as the universe itself. Before we go, I'd love to hear your thoughts. Which of these theories resonated with you the most? Do you think reality is shaped by observation, or is there something deeper at play? Share your ideas in the comments below. I can't wait to read them. And if you enjoyed this journey through the quantum cosmos, don't forget to hit the like button, subscribe for more mind-expanding content, and ring the notification bell so you never miss an upload. Thanks for joining me on this adventure, and remember, the universe is full of mysteries waiting to be uncovered. Until next time, keep exploring.